very important theorem in multivariable calculus. For example, in single variable calculus, we see that if a function has identical zero derivative, then it is a constant function. This is no result in single variable calculus. How about multivariable functions? Okay, so f maybe suppose omega is a subset of Rn, is open subset and convex. F is differentiable at every point. So because it is differentiable, the gradient is defined everywhere. Now we assume that the gradient is 0 in omega. Okay, then f is constant. Okay, this can be proved using the mean value theorem we just established. Okay, here a condition is very interesting. Why we need the domain to omega to be convex? Because if f is not convex, if f is not convex, we cannot compare the value of f between these 2 points, because part of this segment joining these 2 points lies outside the domain omega. Okay, so this is the reason why we need to assume that it is convex. Because of so the proof goes this way. Fix a in omega for x in omega, because omega is convex, then the segment joining ax contained in omega. Therefore, by the mean value theorem, fx minus fa is the gradient of some intermediate point x minus a. But the gradient is identically 0. We assume this is the assumption of the problem. So this is 0, because the gradient is identically 0. So this means fx equal fa. That is, every point, the value of f at every point equal the value of f at a given point a. Therefore, f is constant. So this proof requires that the omega is convex. Otherwise, for some x, the segment between a and x will not contain in omega. So our mean value theorem could not apply, because the theorem requires AB, the segment AB contains in omega. Okay, this is why we need omega to be convex. But I will tell you that even if omega is not convex, the conclusion is still true. If omega is only open and a differentiable function has identically 0 gradient, then it must be constant function. This is also true, but the proof is slightly difficult than this one. So I have a remark here. Even if omega not convex, result is still true. Okay, this can be an exercise for you. Our next example is also important. Suppose U defined in the plane R2 is differentiable and satisfies 2ux plus uy is 0. And also, the value of u at x0 is 0 for any real number x. Suppose a differentiable function u satisfies these two conditions. The first condition is an equality involving the derivatives of u. So if you consider the u as an unknown function, so this is a differential equation about u. Because u is multivariable, and so this is in fact a partial differential equation. Okay, this is the first condition. The second condition means that the value of u on the x-axis is 0. So this is the x-axis. This is the y-axis. So the second condition means that u is 0 on this horizontal line. U equal to 0 here. So what can we say about u? The result is that u is identically 0. Okay. So this kind of problem is very basic. For example, in partial differential equation, you can consider this as a simple question in partial differential equation. But partial differential equation is based on mathematical analysis. So when we study mathematical analysis, we need to develop some idea how to study this question. The idea is, as before, convert the problem into a problem about a single variable function. This is the idea. Convert to single value functions. How to do this? You see the condition here, 2ux plus uy. What's this? 2ux plus uy is ux, uy, and 2, 1. So this is the gradient of u and a given a direction arrow. The component of arrow is 2 and 1. Okay, so this is the directional derivative of u along this direction arrow. Okay, so it is natural to, because of this reason, it is natural to consider u along this direction, along the line in the direction of the arrow. Okay, therefore we consider the line which is direction 2, 1. Because every such line has an intersection with the x-axis. Okay, every such line has an intersection with the x-axis here. But f is here, u is here, u is 0 at the intersection. Okay, if you can prove that u is constant along such line, then because u is constant here, u constant here, u is 0 here, then u must also be 0 here. This is the idea. Very intuitive. But how to motivate this idea? I think that the equation, the left-hand side of the equation, is essentially the directional derivative. This fact is the clue to have this motivation. So how to realize this idea? So we take any point given a b in R2. Here is the point AB. Given AB in R2, we consider the value of f passing this point along the direction 2, 1. I say it again. We consider the value of fu on the line passing this point AB and in the direction of 2, 1. So how to restrict u to this line? Of course, consider phi. Phi t is the value of u at the line passing this point. For those points in this line, x is a plus 2t, y is b plus t, right? Therefore, we consider the value of u at a plus 2t, b plus t. This is what we call restrict u to the line. So this will give us a function of t. We denote it by phi. Phi is a function for every real number t. It is defined in this way. Okay. Now, as I said before, we want to prove that u is constant along such line. So that is, we need to prove that phi is a constant function. Therefore, we take the derivative of phi. Phi prime t. Phi prime t is the directional derivative. We denote L to be 2, 1 as before. Then phi prime t is the directional derivative of u in the direction of L at this point, a plus 2t, b plus t. As you can check, this you can check. The proof of that is similar to the proof here. Okay, you can go like this to obtain this equality here. Okay. Anyway, we have this equality. So now the directional derivative of u in the direction of L is the gradient and is the inner product of the gradient and the L. So this is the gradient of u at this point, a plus 2t, b plus t, and the L. L is 2, 1. And the gradient is ux and uy. Right? The gradient is ux and uy. Therefore, the gradient, the inner product of the gradient and the direction is 2ux, a plus 2t, b plus t, plus uy multiply 1, uy also at this point. A plus 2t, b plus t. Now we can apply the equation because u satisfies this equation. U satisfies the equation given in the problem. We see that 2ux plus uy is 0 at every point. Okay. So this means that the result is 0. By the equation, the result is 0. Therefore, this phi, the derivative of this phi is identically 0. So phi is a constant function. Phi is a constant function. Therefore, our UAB, what's UAB? UAB is phi 0, right? By the definition of phi, UAB is phi 0. Remember, our phi t is u a plus 2t b plus t. So UAB is phi 0. But because of phi is a constant function, phi 0 equals phi minus b. Then in the phi t equal u a plus 2t b plus t, you let t equal minus b, you get u a minus 2b 0. Okay, this is 0. Because our ux0 is always 0. Again, this is a condition given for you in the problem. Okay, ux0 is 0 for every x, right? So in particular, for our x equal a minus 2b, it is 0. So we prove that UAB is 0. But AB is any point in the plane. For every point AB in R2, we can deduce that UAB is 0. Therefore, U is identically 0, and the proof is complete.